Hello and welcome to my YouTube channel. Today in this video we are going to learn how to generate pulse width modulation signal using STM32F446RE microcontroller board. This is the second part of the video. For the first part you can visit my channel and you can get part 8a. Now let's start the video. So to generate pulse width modulation or pulse width modulated signal, we have to follow few steps. First, like I discussed in the previous video, we have to select the appropriate timer, and if needed, we can connect that timer to a particular GPIO pin to generate PWM signal or to see the effect of PWM signal using a CRO or logic analyzer. Then we need to calculate the values for prescaler, auto reload register, capture compare register to generate a PWM signal. If you can recall, ARR will be used to generate the PWM frequency, or we can say frequency of the PWM signal. CCR register's value will decide the duty cycle of the PWM signal. Then we need to configure the basic parameters or above parameters in the STM32CubeMX IDE software. And then we may write a program in the STM Cube IDE to generate the required PWM signal. Now let us go a bit deeper to understand what are the steps required to generate PWM signal using STM32F446RE microcontroller board. First, for the timer selection in this example, I am going to use the timer 2 channel 1 of STM32F446RE microcontroller, because timer 2 channel 1 is connected to PA5 or 5th pin of port A, and PA5 is connected to the onboard LED of Nucleo F446RE microcontroller board. Therefore, I am going to choose timer 2 channel number 1. Second, I will do some calculations using the Excel file that I have created. In the Excel file, you can see I have configured few things, such as, first of all, I will have to provide the clock frequency that I am going to use in the timer. Then I will use a prescaler value to bring down the clock frequency, and after prescaling I will get a particular frequency of the timer clock, and based on the required PWM frequency I can calculate the value of ARR, and based on the duty cycle required I can calculate the CCR value. This Excel file is very easy to create. For example, first of all, you can directly put the value of timer clock frequency that you are going to use in the STM CubeMX. Then you can select a prescaler value. All the green background parameters are the parameters which we have to decide, and yellow parameters are the parameters which will be calculated by the Excel. For here example, you can see prescaled timer clock frequency is calculated by this equation, B3 divided by B5 plus 1. Okay, it is nothing but the timer clock frequency divided by prescaler plus 1. For further details, you can go to the previous video. Then after calculating the prescaled timer clock frequency, we can decide the PWM frequency. In my case, I am using 1000 Hz, which is 1 kHz. Based on these two values, that is the pre-scaled timer clock frequency and PWM frequency, we can calculate the value of ARR. It is very simple. You just have to divide the pre-scaled timer clock frequency by the PWM frequency required. Then after that, we can decide what clock frequency, duty cycle we want to generate. And based on that, we can calculate the value of CCR. For that, you can use this equation where you have the duty cycle divided by 100, because duty cycle is written in percentage. So 50 divided by 100 multiplied by the ARR value. With this, we can easily calculate the value of ARR and CRR. Now coming back to the presentation. Next, we will have to configure the CubeMX, and then later we can write our code. So let us go to the CubeMX IDE and configure all the required CubeMX parameters, and then we will write the code in the CubeMX IDE. So let me just go to File, New, STM32 project. This will allow me to start a new project. Here I will have to select the target, which can be based on the microcontroller unit or board selection. I am going to prefer board selector. So here we can type Nucleo F446RE. So here we have Nucleo F446RE microcontroller board. Click Next and then give a name to the project. So let me give a name to the project. Let it be PWM underscore generation and click Finish. So it says initialize all peripherals with their default mode. No, we don't want to initialize the peripherals in their default mode. It will take few seconds to complete the process and we will get into the CubeMX mode. And you can see here we have entered the CubeMX mode and we can see all the IC's pins are already defined. So let me go to the pinout and clear pinouts. So this will clear all the pins configuration. So we will get a raw IC. So yes, now the IC is completely raw. Like I said, we are going to use PA5 because PA5 provides the connection to the onboard LED. Apart from that, we can see here timer 2 channel 1. So I will select that. So PA5 has been configured and it is configured for timer 2 channel 1. Let me rename it. Enter. For that I can right click and enter user label. I can just say PWM underscore LED. Done. So we have renamed the PA5. Now after this, we may configure the system core where we can see some of the important parameters like debug. So we can go for trace asynchronous SW, and time base will be system. We don't have to change it right now. And done. Then we have to configure the timer. Because we are using timer 2, go to timer 2. First of all, we will have to provide the clock source. So let it be internal clock and enable the channel number 1. And you can go down PWM generation channel number 1. Done. We don't have to configure anything else in this timer 2. For example, now we can come down and provide the details of the prescaler. So from the Excel file, we have calculated the prescaler is 15, or we can say it is basically 16 minus 1. And then it asks about the auto reload value. Okay, auto reload registers value. Let me just make this window a bit bigger. Now auto reload registers value. From the Excel file, we can see auto reloads registers value is 4000 to get a PWM of frequency 1000 Hz or 1 kHz. So let me just put 4000 here. Okay, and that's all. We don't have to change anything else in the configuration here. Okay, now after this we can go to the clock configuration, and now the question comes here, which clock we have to change, because here we can see it shows 84 megahertz in the clocks, timer clock APB1 and APB2. Now the question comes, the timer 2 is connected to which of these two buses, APB1 or APB2? For that, you can open the block diagram of STM32F446RE microcontroller board, or you can download this document from the STM microelectronics website, DS10693 revision 10. Now in this, let me zoom it a bit, and you can see timer 2, okay, has got 32-bit timer. It is a 32-bit timer. It has got 4 channels, and if we come down, it is connected to APB1 bus. Okay, so note this, that APB1 bus is connected to timer 2. So we will have to configure APB1 bus. So here we have APB1 timer clocks. So let me change it to 64 megahertz. Why 64 megahertz? Because you can see here the timer clock frequency was set to 64,000 or 64 megahertz. You may change this value also depending on your choice. So let me just make it 64 megahertz and click enter. So the CubeMX will automatically configure all the lines or all the values for us. Done. So we don't have to worry about the rest of the part. So APB1 timer bus or timer clock is configured for 64 megahertz. Now we can generate the code. For that, you can click on the device configuration tool code generation using this geared button, or you can click save all button. So let me click the device configuration tool code generation. This will generate the C code for us with all the configurations. So let me just show you all the configurations done by the CubeMX. So here we have the configuration for the system clock. Okay, let me minimize it. Then we have the configuration for timer 2. We can see here timer 2's prescaler is configured to 16 minus 1. It is counter mode in the up direction, that is up counter. 4000 is the period, and so on. So let me just minimize this window also, or you can just right click and go to folding and collapse all. So this reduces the codes and or collapses the codes. So now we have to write our code in this skeleton. So let us start filling up the codes. First of all, we will have to create two variables. So let me go to the user code. Okay, user code begin. Here we have the user code. Remember, always enter the code in between these limits. Otherwise, whenever you will update anything in the CubeMX and regenerate the code, everything will be deleted. So keep your code within the user limits. Okay. So we can first of all start writing the code in the private variable. So uint control space 16t. This will be a 16-bit unsigned integer. Let us call it duty cycle. Okay. Then we can use uint 16 underscore t, 16-bit unsigned integer value for pin state. Okay. This will help us to generate the or visualize the code in the STM cube IDE itself. These two variables are enough. Then we can come down and let me check. Private user code begin here. Okay. So here we can see the timer has been started by the system. Let me just open that part. So you can see here the system clock configuration initialized, and wait a second. Yeah, this is the timer handle, and now we can start our main code. In the main, just a second. Okay, so here in the section user code begin to, we can start writing the code. So we have TIM, okay, 2, timer 2, because this is the timer we are using, timer 2, and we are going to use CCR1, okay, and put the value that we have calculated from the Excel. So CCR value is 2000, so I will put 2000 to get a 50% duty cycle. Then I can start the timer. So hall underscore tim control space underscore PWM, and we can go down and click start. So it requires two arguments. So the handle of the timer, done, and the channel. For the channel we can use timer underscore channel 1, done. So if you want to know what are the arguments that we can pass here, okay, then HTIM2. So how to know the arguments, or what are the valid arguments that we can pass in this function? So for that you can select this function, right click and open declaration. This will show you what are the arguments allowed in this particular function. So first it shows that you have to pass the handle of the timer. Okay, and then you can choose the channel. There are 4 channels allowed in timer 2. Okay, so timer 2 has 4 channels. You can choose any of these channels. Because we have configured for timer 2 channel 1, we will use TIM channel 1. Okay, so now after this we can just go to the loop, while loop, and just inside this user code begin 3 we can write the rest of the code. So pin underscore state is equal to hall underscore GPIO. We are going to read the GPIO pin, and we can give the port name. So if you can recall, PWM LED port. Okay, and then we need to provide the pin details. So it is PWM LED pin. Okay, which is PA5 basically. Done. And let us give a very small delay for the whole loop. Let I keep it 5 or 1 microsecond. That is enough. 1 millisecond, my mistake. Okay, so 1 millisecond. So this will provide a delay of 1 millisecond. Okay, done. So this is all the code that we have to write. Because let me repeat. First of all, we have created 2 variables. One will keep the value for duty cycle and another for the pin state. Then coming down, we have provided the value for CCR register, and then we started the timer. After this, the PWM signal will be generated, and we can see the effect of PWM signal on the onboard LED. We are also passing that value to the pin state variable, and we are providing a very small delay. Okay, so let me just build the program by pressing this hammer button, and you can see we have 0 errors, 0 warnings. So let me connect the board and debug the code. So before debugging, let me go to the debug configuration. Click here, and in the debugger, do check few things, like you have to select the local GDB server. Okay, come down and enable the serial wire viewer, and it has automatically checked what is the clock frequency. So 64 megahertz for the SWV, that is serial wire viewer. Click on the enable live expression and debug. So this will start the debugging process. Okay, let me show you one more feature of the STM Cube ID. So right now the program is waiting for the run command, or it is paused here at the all init function. Okay, so go to window, show view, SWV, go down, SWV data trace time graph. Okay, so we have SWV data trace timeline graph. Click on this config trace button. Here you can put the variable name pin state. Okay, so that we can check what is the state of the pin. This will show you the PWM signal generated at the pin. Okay, and click this button, enable the comparator 0, and click on the 0 button here and click OK. Now after this, click the red button, start trace. Apart from that, you can see the live expression. So let me just drag it out, click on the live expression. Let me remove these values. So we have pin state, and in this pin state we can see the live expression whether it is 0 or 1, and click on this red button and then click on resume. With this we can see the graph is generated. Now we can see it is a 50%, almost 50% duty cycle. To change the duty cycle, let me just stop the program. Okay. To change the duty cycle, we can go to the Excel file and let me make it 10% duty cycle, enter. And now we can see CCR value is 400. So let me just modify the code. So go to the CCR value. Instead of 2000, we can put 400. Okay, rebuild the program, debug the code. And click on the SWV data trace timeline graph and click resume. Resume, and you can see the waveform generated by the microcontroller. Now how to verify whether this is perfectly 10% duty cycle or so? For that you can use either DSO, digital storage oscilloscopes, or logic analyzers. So here I have a logic analyzer. Let me run the code again. Okay, resume the code, go to the logic analyzer and click OK, measure. So now here you can see the frequency is 1 kilohertz. Okay, and duty cycle is 9.9%. Or you can just click on this add measurement from here to here, and you can see here the frequency is 1 kilohertz and the duty cycle is 9.995. It is almost 10% duty cycle. Or if you want to change the code, so you can go to the Excel file. Suppose I want 30% duty cycle. Now the CCR value is 1200. I will go to the code. In the main file, I will just change the value to 1200. 1200. Rebuild the program. Debug the program. Okay, and then again we can see the SWV data trace timeline. Resume the code. Wait a second, something has mismatched, I think. Let a second. Okay, capture the signal using logic analyzer, and we can see from here to here we have 1 kilohertz frequency of the PWM signal, and duty cycle is 29.994%, which is 30% duty cycle. Now with this, I would like to conclude the presentation. If you have any suggestions or opinions, please share your suggestions and opinions in the comment section. If you have not subscribed my channel, then I would request you to please subscribe the channel and press the bell icon so that you will get the updates as soon as I upload a new video. If you like this video, then do press like button. Thank you and have a nice day.